Hi kids, Mrs. Geiger here, with our very favorite molecule, water. And some people were asking me some questions about why acids are electrolytes, even if it looks like they're covalently bonded. So I want to go back and review a little bit about what makes some substances dissolve in water and what makes some substances insoluble in water, and then look at what those solutions look like, because those solutions are important. So what you really need to know about water is that water is polar. Oxygen is negatively charged and the hydrogen side ends up being positively charged. And we know that because we can draw a Lewis electron dot diagram of water. And when we do this Lewis electron dot diagram of water, we know that hydrogen has a very low electronegativity and oxygen has a much larger electronegativity. So these electrons, although they're shared, they're going to be much closer to the oxygen atom than they are to the hydrogen atom. And that's because hydrogen has such a low electronegativity compared to oxygen. Remember when we look at the periodic table, how we always said that hydrogen was a weirdo. The reason we say that, and the reason that hydrogen is not touching the rest of group 1, is because although hydrogen has one valence electron and is a nonmetal, it very often acts like other group 1 elements. So it easily gives away its valence electron in order to become stable, and therefore just becomes a proton. All right, so let's think about some things that water can dissolve. Here's what glucose looks like. You're going to remember that glucose is C6H12O6. So glucose is a really big molecule. You should also notice that because of these oxygens, a glucose molecule is polar. So glucose, sugar, will dissolve in water because it is polar. But when sugar dissolves, it does not dissociate. So the glucose molecules are going to spread out in solution, but they are not going to dissociate. That means that glucose is not an electrolyte, because this neutral molecule here, as it dissolves and spreads out, does not create any moving charged particles. So I have another diagram here. And what you'll see at the bottom here is that what we've done is taken this shape of our glucose. This is the ball and stick model. In this organic molecule, in this picture, what you don't see, what we don't write, is that on each of these corners, there is an atom of carbon. So these blue atoms here are actually here on the corners. And this is called an organic molecule because it is made out of mostly carbons, but also oxygens and hydrogens. So glucose is an example of an organic molecule. This model shows a different configuration of glucose, and that is called an isomer. So these are isomers of each other. Now, I'm getting a little off topic because you don't need to know this, but what you should see is that these both have C6H12O6. Oh, I'm missing that carbon right there. This guy. C6H12O6. So in this diagram, we've taken that shape and we're just showing it as that little hexagon there. So what you should see is here that this is a sugar crystal with all of those glucose molecules, and they are in a fixed geometric pattern. But when the water molecules come and they pull apart the glucose, it dissolves, but it does not dissociate. All right, so that happens because the molecules are polar, but the reason that it doesn't dissociate is because it is a molecule. It is covalently bonded. I'm going to scroll up here because in this diagram we have here salt. So this represents sodium chloride, NaCl. And what you can see in this is that the NaCl, what you can see is that my negative chloride ions and my positive sodium ions are attracted to each other when they're in the solid. So when they dissolve, they do dissociate. They do break apart into their positive ions and their negative ions. So that means that NaCl is an electrolyte because now these moving charged particles will allow electricity to be conducted through this substance. So acids are electrolytes because hydrogen has such a low electronegativity. Bases are electrolytes because they are usually ionic substances. So, for example here, if we take our most common acid that we're going to be talking about, which is hydrochloric acid, HCl. All right, and if I was to draw, it would look like this, right? A hydrogen atom bonded to a chlorine atom. Now we would expect this to be covalently bonded in a molecule because hydrogen is a nonmetal and chlorine is a nonmetal. But remember, hydrogen is a weirdo, and hydrogen easily gives away its valence electron to chlorine. So if I draw the Lewis electron dot diagram of this, 1, 2, 3, 4, 5, 6, 7 valence electrons, and I draw my hydrogen here, because of hydrogen having such a low electronegativity, this, when it dissolves, will dissociate. And when that happens, I'm going to end up with my H plus ion, and I'm going to end up with a chloride ion. So acids are special. They dissociate and they form ions, which makes them electrolytes. Now, our most common base is sodium hydroxide. Sodium hydroxide is already, ionic. You know that because it's made out of a metal and a polyatomic ion. So, when this gets into water, it is definitely going to break apart into the sodium ion and the hydroxide ion. All right, so bases typically are already ionic, but acids, the reason that they form ions is because of hydrogen. Hydrogen acts like a group 1 element even though it is a nonmetal. So that brings us to our next definition. Bronsted and Lowry actually worked separately from each other, and they came up with the same conclusion, so their names both get to be on the theory. So for acids, we're going to talk about acids as donating a proton. So remember that a proton is the same as a hydrogen ion in solution, as the same as a hydronium ion. So I'm just going to jump down to this slide where we talked about this, where a hydrogen ion can also be talked about as a proton. So Bronsted and Lowry's definition uses the term proton instead of hydrogen ion. So we're going to say that acids are substances that donate a proton. In an aqueous solution. So really it's the same definition as before, but when we do our example here, when we talk about Bronsted and Lowry, very often we're going to use 2 water molecules because you can also say that an acid increases the hydronium ion concentration. So our example of this here is going to be that if water reacts with HCl, it is going to form H3 3O plus, and Cl minus. Now, of course, all of those are aqueous. So the reason that we say that an acid donates a hydrogen ion or donates a proton is because this hydrogen, this proton that was part of the hydrochloric acid, was donated to the water molecule to become a hydronium ion. All right, so we're going to use this terminology that it donates a proton. So there's some substances that Bronsted and Lowry looked at that made them go, that's odd. They looked at some substances that, although are bases, although they turn litmus and red cabbage juice blue, they have very high pHs, they're not ionic. And they wanted to know how that worked and what was happening here. So we're going to take a look at our example of ammonia. All right, we'll go back and write the definition in a moment, but first we're going to, I'm just going to scooch down here where I have a little bit more room, and we're going to talk about ammonia. Ammonia, you should know, has the formula of NH3. So what would happen if NH3 reacted with water? So let's go ahead and draw the Lewis electron diagram for NH3. You should remember that ammonia is polar because it has this lopsided shape to it. Now, if a water molecule is made out of hydrogen and oxygen, and it looks like this, we know that this hydrogen is positively charged. So if we know that the hydrogen here has a partial positive, and we also know that this molecule of ammonia is negatively charged up here, and these are positives, which part of the water molecule is going to be attracted to the ammonia? That's right, this positive hydrogen here. And guess what? Oxygen is so strong that it's going to hold on to these electrons, and hydrogen is very satisfied with that because there are 2 electrons here. Remember, hydrogen needs 2 electrons to fill its duet, its valence orbital. So it can do that here. It can leave the electrons behind and jump over to this molecule here, which will make a stable ion. So what do we end up getting when the hydrogen goes to that ammonia? What we end up with is a ion called NH4. It still has a plus charge because the hydrogen brings its proton. Remember, this is a proton, but it doesn't bring any electrons, so it still ends up with a positive charge. So when that happens, I'm going to go ahead and draw that. Right, I'm going to take this hydrogen and I'm going to move it over. Let's see if oh no, it's all together. So I need to erase that guy. All right, and I'm going to go ahead and redraw that same hydrogen here. All right, and now I have an ion. And this ion ends up with a positive charge there. But what happens here? That's right, we end up with an ion here as well. This is an ion because it has that extra hydrogen electron there. So this is also an ion. And you should recognize that that is a hydroxide ion. So what Bronsted and Lowry realized is that sometimes bases increase the amount of hydroxide that's in solution Not because they have a hydroxide in their structure that they're giving away, like sodium hydroxide or calcium hydroxide or magnesium hydroxide or any of the other metals bonded to a hydroxide ion. Those bases give away a hydroxide when they dissolve because it's part of their structure. But what Bronsted and Lowry figured out is that some substances actually increase the hydroxide ion concentration by taking a hydrogen off of a water molecule. And the hydroxide is what's left behind. So what they said is that this NH3 is accepting a hydrogen ion. It is accepting the proton. All right, so instead of giving it away, it's taking one on. So this NH3 here, this ammonia, is what we call a proton acceptor. It gained a proton to go from NH3 to NH4 plus, and it left hydroxide as a result. So Bronsted and Lowry redefined bases to be defined as substances that accept a proton in an aqueous solution. All right, and so our example was what I drew down below with the ammonia and ammonia and you should recognize this NH4 ion. That ion is called ammonium. So it's called ammonium because it came from ammonia, and this OH minus you should recognize is called a hydroxide. All right, one more definition. So Lewis, remember Lewis? Yeah, Lewis made all those dot diagrams, right? And what were the dots in the dot diagram? Electrons, you got it. So what Lewis said is, guys, we're talking a lot about protons, but we all know that bonding doesn't have to do with protons. Bonding has to do with a change in the electrons. So Lewis looked at this in a little bit of a different way. I'm going to put up the reaction that's occurring all the time in water. If two water molecules react, two water molecules bump into each other. Some of them are going to ionize. Some of them are going to lose their hydrogen ion and become a hydroxide. And some of them are going to gain that hydrogen ion and become a hydronium. So we're going to end up with two different ions. We're going to end up with an H3O plus and an OH minus. Now, let's talk about what those all are. So we know that these are water molecules, right? And we know that this is called a hydronium. And we know that this is called a hydroxide. But one of these water molecules is acting like an acid. One of these water molecules is giving off a proton. And the other one is taking on that proton. So what Lewis said was, how about instead of acids being defined as substances that donate a proton, he flipped it. So instead of giving away an H plus, he said that they are actually taking on an electron. So acids accept an electron, and bases, he said, instead of taking on or accepting a proton, let's flip it and say that bases donate an electron. Now, Lewis's definition of acids and bases is not on the Regents exam, but it's useful to know because when you get into higher level chemistry, what you'll see is that people talk about Lewis acids and bases a lot more because, right, bonding has to do with electrons much more than the movement of protons. But you should know the names of these ions, and you should realize that this is always happening in water, but only in 1 out of 1 times 10 to the 14th water molecule. So 1 out of every single one of them is at any given time dissociated in this way. All right. So H3O plus here came from H2O. So H3O plus, did it take on a proton or did it give away a proton? That's right. It took on a proton. So that means that in this is a reversible reaction. So in the forward of this reaction, if this water molecule here took on an H plus, accepted an H plus, is it acting as an acid or a base? That's right, it's acting as the base. So this water molecule here is acting as a base, but in the reverse reaction, this is going to be giving away its H plus, so this acts as an acid. Now the other two, though, this water molecule gave away its H plus, so it gives off its H plus. So in the forward reaction, this acts as the acid. And in the reverse of this reaction, when the OH goes back to being water by gaining the H plus, this acts as the base. These are called conjugate acid-base pairs, another concept that is not on the Regents exam, but you will need to know it when you do higher level chemistry. You should know that in this, there's always going to be an acid and a base on either side of the reaction, and if a substance is a base in the forward reaction, it's an acid in the reverse. And the opposite is true of the other substance. If it's an acid in the forward reaction, it's a base in the reverse.